Hi everybody, this is the next in a series on fluid mechanics, again looking at the idea more of static fluids. After discussing the ideas of density, buoyancy, and fluid pressure, I want to look at something specific to the idea particularly of fluid pressure, and that is something called Pascal's Principle. And in Pascal's Principle, we're looking at the fact that when you already have a fluid and now you're going to add some additional pressure onto the fluid itself. Now, first of all, there's an interesting thing about fluids in that all fluids will seek the same height as long as the pressure is uniform on them. So this picture here, which I always find kind of interesting, it shows a container with a fluid in it, and the shapes of the containers are all very different. They all have different volumes and shapes and sizes, yet the fluid level on each one is all at exactly the same height. And that's because they're all feeling the exact same pressure above them, which is air pressure. So that's what's sort of important to keep in mind here, is that the downward pressure on each one of these fluids is still atmospheric pressure. And so that means that it'll stay at exactly the same level, regardless of what their shape actually looks like. And again, this sort of gives an idea of this. If you look at these two containers here, they have similar volumes in terms of this, but their shapes are very, very different, and their cross-sectional areas are different. So if I have a fluid in here, and the pressure at one end is the exact same pressure over here, and again, that's because they're feeling the exact same pressure on top of each other. So if I add more water to one side, the other side fills up to the exact same level. And again, that's because the pressures that they're feeling from the air on both sides are exactly the same. What Pascal's principle has to do with is when you apply another pressure to the fluid, an external pressure. So what's interesting is Pascal saying that if you press down on a fluid at one place, that pressure you're applying there is then transmitted to all points in the fluid equally. And sort of what does that really mean? If we take a look at these two water tanks here, again, which have very, very different shapes. And for the moment, let's just turn the atmosphere off to make this look a little easier. So if I go to the pressure at this line right here, which is about 12.5 kilopascals. If I come over here, it's also 12.5 kilopascals. Now the idea here is if I add pressure to one side here, coming back to this part of the tank, if I add weight onto this, that adds pressure there, and that pressure now increases the overall pressure inside the tank. So you notice that additional pressure that we're adding down on here has added almost another kilopascal of pressure to this point on the tank. But what's kind of neat is over here it's done the same thing. So that additional pressure inside here causes an additional pressure outside here, even though now these two things are different. Now, that's also what's important. The pressure on this side is greater than the pressure on this side because this is having zero pressure actually acting on it because I took out the atmosphere. So that caused, of course, the whole water level here to rise. And that'll sort of bring up another aspect that's really interesting about Pascal's principle. So the important thing to keep in mind is when you put pressure on one part of a liquid, that pressure is equally distributed through all parts of the liquid. So, which means what we would call the absolute pressure, what I kind of just showed you there, would consist of atmospheric pressure if there's air involved, however deep you are in the liquid for its own fluid pressure, plus any additional pressure that you've sort of added on there. Just like I showed by putting on that weight on there, creating an additional kilopascal worth of pressure on top of that liquid. What this really is important to is the idea of what's called a hydraulic lift. This also can be applied to what's called a pneumatic lift. Hydraulics means using a fluid, pneumatics means using a gas, like air. And the idea behind a hydraulic lift is that the change in pressure on one point has to be equal to the change in pressure on the other point. Okay, so now again, what does all this mean? As I kind of showed with that demonstration, if you apply a force to one side of a liquid, you are creating a change in pressure, which will be based on that force over the cross-sectional area of what you are applying to. Now over here, whatever that change in pressure is on this first part, you're going to have a change in pressure over here, which would also be a force over its area. And again, as Pascal's saying with his principle, that the change in pressure in one point has to be the same as the change in pressure in the other. Now, the interesting thing about this, about how a hydraulic lift then works, is I can say that the force on one side over the area it's applied has to equal the force on the other side over its area applied. And what this means is that I can have a small area which will take a little bit of force, and then if I make a larger area on the other side, I actually can lift more material. And I know that sounds a little strange and confusing, so let's look at what an example means. So here's the idea of a hydraulic lift. I've got a 1,000 kilogram car on a hydraulic lift. Now again, the way the hydraulic lift sort of works is you apply a force to a small area. That pressure is then applied to a very large area, allowing you to lift something. So the question is, if I want to lift a 1,000 kilogram car, how much force would I need to apply? If we keep in mind the fact that whatever change in pressure we do on one side is the same as the change in pressure on the other, force over the area on one side must equal the force over the area on the other side, which means that the force we have to apply on the small side would be the ratio of areas times the force on the second side. Now, what's the force on the second side need to be? Well, if I'm lifting something, obviously what I'm countering or lifting is the weight of this car. That means that the force I'm applying is the first area, the small area, which is 5 times 10 to the minus 3 square meters, over the larger area, which is 0.1 square meters, times the weight. And the weight would be the mass times gravity. So think about this. We're lifting what is the equivalent of a 10,000 Newton car. So we want to know how much force that's going to be. Well, it turns out I only need 500 newtons of force, which is significantly smaller than the weight of the car. And so that's a pretty neat thing, that you can use a fluid and a small amount of force to lift something that is really, really heavy. And so that's really the way a lot of hydraulics really work. And that goes into a lot of machinery and everything like that that allows us to do this. And the most important part is, one, you go from a small area to a large area. Okay? The small area needs a small force. The large area then can apply a large force. And the key, again, to Pascal's principle is going to be the fact that whatever pressure you apply to the one area is equally applied in all other places. So by adjusting the area, you then adjust the amount of force. And that's basically the idea behind Pascal's principle. All right, see you next time.